Dear students, today we will be discussing about testing of solar air heater and application of solar air heaters in drying and electricity generation. So, this figure shows the experimental setup by which solar air heater can be tested. So, it is a closed loop consisting of a solar air heater. This is the solar air heater. One blower is required to blow air. This is the blower. Of course, we need measurement instrument. So, this is a manometer. This is a manometer, and we need flow measuring device, maybe mass flow meter, or maybe rotameter. So, I am talking about very sophisticated mass flow meter, or maybe rotameter can be used for measurement of flow. And we need a air reconditioning apparatus, because we need to perform the experiment at constant TFI. Okay? As you can see, there are positions to measure the temperature. So, these are the thermocouple sensors position. Okay? So, we can average it out later on. So, once we know the temperature at different locations. And also here we need to have some kind of mixing vents, because this is air. Okay? So, at different locations temperature variation will be there. So, we need to use this kind of vents to make uniform temperature. Then only we can attach this thermocouple sensor for measurement of temperature. Okay? So, as a whole, here this air inlet is here and outlet is here, and then this air again flow through the same circuit, but conditioning has to be done. Okay? Because this air will be passing through this tube at TFI, that has to be fixed. Okay? That is why this air conditioning apparatus is installed here. Okay? And we need to vary this mass flow rate. Okay? So, we need to perform here at different mass flow rate, means this characteristics of this solar air heater is to be performed at different mass flow rate. So, which is different than in case of liquid flat plate collector. And while doing the experiments, we need to do some kind of precautions. Say for example, this exit air has to be well mixed before the temperature is measured. Okay? So, this mixing is done with the help of vents, as I have shown here, and this temperature need to be measured at different locations across the duct cross section. Okay? Because of this non-uniformity of the temperature. Okay? And this setup works in a closed system. Okay? Now, if you see this typical performance curve of the solar air heater, you can see these two are at different mass flow rates. Okay? And this is the experimental results of Gupta and Garg, and as you can see, there are scatter of data, and this scatter is very, very large. Okay? And in case of liquid flat plate collector, what we were doing, only single mass flow rate was giving the entire characteristics of the liquid flat plate collector. But in case of solar air heater, this is not so. So, we have to perform the experiments at different mass flow rate. Okay? So, why this is so? If we compare both liquid flat plate collector and solar air heater, so in case of liquid flat plate collectors, changes in the value of mass flow rate do not appreciably affect the performance because of high values of liquid side heat transfer coefficient. Okay? That is why a single test curve is therefore generally adequate for predicting the behavior of such collectors. But in case of solar air heaters, the changes in the value of mass flow rate appreciably affect the performance, because the value of air side heat transfer coefficient is relatively low. Okay? This is the primary reason. So, in order to obtain complete information on a solar air heater, it becomes necessary to conduct test over a range of mass flow rates, with each flow rate yielding its own efficiency curve. Okay? So, that is why we need to perform the test at different mass flow rate, okay, keeping the inlet fluid temperature constant. Now, let us take an example to calculate efficiency of a solar air heater and the corresponding mass flow rate under given set of operating conditions. The example goes something like a solar air heater of length L1 is equal to 1.2 meter and width L2 is equal to 0.9 meter is tested under a range of flow rates varying from 25 to 200 kg per hour, and the efficiency curve so generated is shown in figure 1. So, we need to calculate the efficiency and the corresponding mass flow rate under the condition like air inlet temperature of 54 degrees C, air outlet temperature of 74 degrees C, ambient temperature of 26 degree Celsius, and the solar flux incident on solar collector phase is equal to 950 watt per meter square. So, let us solve this problem to solution. All right. The figure what you have seen here, it is efficiency curve which is plotted based on the observer plate area. What you can see here, the variation of instantaneous efficiency with respect to this parameter TF average minus TA to the incident solar radiation flux. Okay. So, with increase in mass flow rate, how this efficiency curve changes, that can be seen here. Okay. Now, it is given that TFI is equal to 54 degrees C, then TFO is equal to 74 degrees C, ambient temperature TA is 26 degrees C, and IT, the amount of solar flux which is falling on the solar air heater, which is given as 950 watt per meter square. So, which is equal to 0.95 kilowatt per meter square. So, why we have converted to kilowatt per meter square? Because if you see the horizontal axis of this efficiency curve, so this IT is in kilowatt, right. Now, let us calculate first the average fluid temperature. Okay. So, T F bar, which is nothing but average fluid temperature, okay, and which can be represented by TFI plus TFO divided by 2. Okay. So, if we substitute the value of TFI, which is equal to 54 and then TFO 74 divided by 2, which is equal to 64 degree Celsius. Okay. So, for the given condition, the x axis parameter, so I will write for the given condition the x axis or the horizontal axis parameter which is nothing but T F bar minus TA to IT, which will be equal to 64. TFI we have calculated to be 64 minus TA is 26 and IT is in kilowatt, it will be 0.95. So, if we do the calculation, it is found to be 40 degree C, it will be in meter square because it will be kilowatt. So, unit will be something like this. Okay. Now, what we need to do? We need to do a trial and error procedure in order to find out the required values of instantaneous efficiency and mass flow rate, right. So, if we see this 40 here, okay, this parameter is calculated to be 40 in our case, and if we consider this mass flow rate, okay, maybe 25 if we consider initially, then we have to find out the cross section point here. So, 40 it will go here and it will cut here, right. So, if we draw a line something like this, okay, so we can find out the corresponding value of the instantaneous efficiency, right. So, now let us do the calculation. So, first let us assume m dot, which is mass flow rate, equal to 25 kg per hour. Okay. So, from the efficiency curve, okay, so we can find out the point, because this point is known by using this plot. This is at 25 kg per hour, first line, followed by 50, then 100, 150 and 200. So, we know this value and we have find out this cross section point, and then corresponding efficiency we need to find out. Okay. So, at the x axis parameter TF bar minus TA IT, which is equal to 40 degree C meter square per kilowatt. So, this efficiency is found to be 24.2%. Okay. So, if you use a scale and take the point, then what we will get, eta I is equal to 24.2%. Okay. And this is nothing but the instantaneous efficiency at mass flow rate of 25 kg per hour, right. Again, we know instantaneous efficiency eta I can be defined as useful heat gain to heat supplied, right. Then what we can write here mathematically, Qi by Qu by heat supplied is nothing but IT multiplied by AC. So, this I is nothing but solar radiation incident on the solar collector, and AC is the collector area, right. So, if we are interested about Qu, then Qu will be something like eta I multiplied by IT multiplied by AC, right. Now, we know the value of instantaneous efficiency at 25 kg per hour, which is equal to 24.2%. So, we can write 0.242, right. So, 24.2 divided by 100, it will be 0.242 multiplied by IT is 950, and area of the collector is 1.2 multiplied by 0.9. Okay. So, if we do the calculation, then QU is found to be about 248.3 watt. Okay. So, this is at mass flow rate of 25 kg per hour, right. Also, we know we have QU is equal to mCp dt, right. So, this is nothing but useful heat gain, can be represented in terms of mass flow rate, specific heat and temperature difference. Okay. So, from this what we can calculate is the mass flow rate, okay. So, which will be equal to QU by Cp multiplied by dt. So, if we substitute these values of QU, Cp and delta T, then we can find out what is m dot. So, QU already we have calculated, which is equal to 248.3 divided by Cp is 1.007 multiplied by 74 minus 54, okay, and we need to multiply this in 10 cube because this is in kilojoule per kg per degree temperature. Okay. So, again we need to multiply this with 3600 because we want m dot in kg per hour, right. So, this will be equal to 44.38 kg per hour, right. So, m dot is found to be now 44.38, but what we did, we initially assumed that mass flow rate is 25 kg per hour, but what we got, it is 44.38. Then we have to see what will be the appropriate mass flow rate. Now, let us assume this m is equal to 50 kg per hour, okay, and let us do the calculation what happens. So, this m dot is now 50 kg per hour, okay. So, this is the assumption we made. So, at this mass flow rate, we get a value of eta I is equal to how much? So, here we have to extend this curve till here, okay. So, this is the curve and then we have to extend this, okay. So, if we do a very precise calculation, then this value is found to be about 28%, okay. So, of course, that has to be at 40 degrees C meter square per kilowatt, okay. And we know QU expression what we have used earlier, which is nothing but eta I multiplied by I into AC, right. So, if we substitute the values of instantaneous efficiency, which is 0.28 multiplied by 950 and then AC is 1.2 meter by 0.9 meter, right. So, if you do the calculation, this QU is found to be 287.3 3 watt as per my calculation. So, QU is found to be this one, right. And also we know QU is m dot Cp delta T. Okay. So, this m dot we can calculate QU by Cp into del T, right. So, this is Cp is the specific heat of air, and this value is also known to us, and QU is also known, which is equal to 287.3 divided by Cp is 1.007 into 10 cube, and delta T is 20. Straight away we can write, which is nothing but 74 minus 54. Okay. So, if we do the calculation, then m dot is found to be 51.354 kg per hour. Okay. So, since the value of m dot calculated from the useful heat gain rate does not match, let us now assume a value, say m dot is equal to 51.354 okay, kg per hour, right. So, we have initiated with 50 and we got 51.354, which is not exactly matching. Then let us try one more time by considering m dot is equal to 51.354 kg per hour. Okay. Now, let us do the calculation. If we see the efficiency curve again, now what happens? We are now interested about 51.354. Okay. So, we will extend this curve, and this is for 50, and 51.354 is in between 50 and 100. Okay. Value will be somewhere here. So, we need to do the interpolation, right. So, how to calculate? By using interpolation, we can calculate eta I at 51.4 kg per hour and at, of course, x axis parameter by IT, which is equal to 40 degree C meter square, then kilowatt. Okay. So, at this condition we need to find out this instantaneous efficiency. Okay. So, how we can calculate? See here, already we know this efficiency, which is equal to 28. So, we will use this, and then efficiency is increasing with increase in mass flow rate at that particular condition. Okay. So, we will see the difference here. So, if we consider here maybe at this condition. Okay. So, interpolation you can use it. So, like something like you can use 30 minus 28 divided by 100 minus 50, okay, and here 51.354 minus 50. Okay. So, here if we draw this line is this is 100. So, this is somewhat higher. Okay. So, it will be, this is for 25, 50, then we have 100, okay, and this will be about 31.5 something. Okay. So, if we do the calculation, so it is about 28.05. Okay. So, that much of instantaneous efficiency we will get. And once we do this, then what we can calculate, we know Q is equal to eta I, then I t, then A c. Okay? And if we substitute the values of eta I, which is equal to 0.2805 multiplied by I t is about 950, then A c is about 1.2 and 0.9, which is equal to 288.2034, okay, to be precise. So, that much of what we will get is Q, right. Now, we know Q is equal to m dot Cp dt, okay, and from here we can calculate m dot, which is found to be 51.516, okay, which is in kg per hour. The m dot assumed earlier, which is equal to 51.354, okay, which is very close to this value, right. So, we can accept this value as the solution to the problem, right. So, this is the procedure by which you can calculate the instantaneous efficiency and mass flow rate. Okay. So, sometimes if we can use a scale and all, then from that also you can calculate what is the instantaneous efficiency at this condition, and finally, we can use Q, and once you know the Q, then by using the expression Q is equal to m Cp dt, and from that we can calculate what is mass flow rate. Okay. And in this case it is found to be 51.516, which is very, very close to the assumed values. Okay. So, this may be the solution to this problem. Okay. Now, let us discuss about solar drying of agricultural products. Okay. The use of solar radiation for drying is one of the oldest applications of solar energy. Solar drying has not yet been widely commercialized because of many issues, and these solar dryers are generally of small capacity. The design of solar dryers are based on primarily empirical and semi-empirical data than in the theoretical design, as you can see many of the cases. The majority of the solar dryer designs are used mainly for drying of various crops, either for family use or for small scale industrial production. So, without delay, let us discuss about drying principles. So, as you can see in this figure shows the process of moisture removal from a solid by using thermal energy input. So, energy input is there, which is thermal, and this is the product which is to be dried and moisture has to be removed. Okay. So, during this phenomenon, hot air is applied and heat and mass transfers are involved throughout this drying process. Okay. The large portion of energy consumed during drying is for transforming liquid water into its vapor, okay, because as you know, it is latent heat of vaporization at this ambient. So, that has to be removed. Okay. The water may be contained in various forms, maybe free water or bound water, okay, which directly related to the drying rate. Okay. This free water is regarded as unbound and the product is non-hygroscopic, and this bound moisture is trapped in closed capillaries in that material, and the material is called hygroscopic. Okay. Now, this moisture content is expressed either on dry or wet basis. So, on dry basis, it is expressed as the ratio of weight of moisture content per unit of wet material. Mathematically, it can be expressed as W is equal to MW to MW plus MD, that means kg per kg of mixture. Okay? So, MW is mass of water and MD is mass of dry solid. And if we are interested about dry basis, okay, so on dry basis it is expressed as the ratio of water content to the weight of the dry material. Mathematically, it can be expressed as X is equal to MW to MD, okay, which is kg of water per kg of dry material. Normally, agricultural products are analyzed based on weight basis, and when mathematical calculations are involved, then dry basis calculations are considered. Now, let us discuss about drying rate, which is very important and is determined by the temperature and moisture content of the product, as well as the temperature, relative humidity and velocity of the drying air. As you can see here, this is a drying curve. So, there are different regimes A, B, then B, C, C, E and E, D. Okay? So, this B to C, this phase 1, C to E phase 2, then E to D is phase 3. Okay? So, here AB is the time spent to heat up the material until the drying temperature is achieved. So, this is first drying temperature has to achieve. So, this is the time spent to heat up the material until the drying temperature is achieved. So, this may be the drying temperature. Okay? So, here horizontal axis is the drying time and vertical axis is the drying rate, right. Then BC is the constant rate drying. So, this part is the constant rate drying. So, it is at constant temperature drying will take place. Okay. So, this phase 1 is nothing but constant rate drying. Okay. Then CE is the falling rate drying, where flow of moisture from mass interior is decreased continuously. Okay. So, when moisture is removed from the surface, then phase 1 is applied. When this moisture has to be removed from the interior of the material, then this pattern follows. Okay. That is falling rate drying follows. And this point E, there is still moisture inside the product, and moisture removal takes place slowly by diffusion, and drying can stop at point D. So, this is the process of diffusion. So, even though this point achieved, okay, further drying might be required in some cases to reach to this point D. Okay. The drying period of these regimes, this phase 1, phase 2 and phase 3, that is constant rate drying, then falling rate drying and second falling rate drying for hygroscopic products depends on the initial moisture content and the prescribed moisture content for safe storage, which is very important. Okay. So, this drying rate curve is important to understand how this drying is taking place if we consider any substance. Okay. Now, we need to learn what is water activity and why this is important. Okay. This water activity is of great importance for food preservation, as it is a measure and a criterion of microorganisms growth and probably toxin release, of enzymatic and non-enzymatic browning development. So, as you can see, this is the mathematical expression by which we can calculate what is water activity. So, Pw is the partial pressure of water solution, then Pw star is the partial pressure of pure water at the same temperature, right. And for every food or agricultural product, there exists an activity limit below which microorganisms stop growing. Okay. So, for example, or for informations, the majority of the bacteria grows at an activity of 0.85, and mold and yeast grows at about an activity of 0.61, and fungi grows at about an activity less than 0.7. So, normally in drying of many agricultural products, the activity is maintained below 0.6. Okay. Also, we need to learn equilibrium moisture content, which is important to understand at what moisture content we need to maintain for a particular product. The equilibrium moisture content refers to the moisture content when the vapor pressure exerted by the moisture of the product equals vapor pressure of the nearby ambient air. Okay. So, this is very important to know this equilibrium moisture content. Also, sometimes we need to know sorption isotherms. Okay. These sorption isotherms are graphical representation of the relationship between the moisture content at the corresponding water activity over a range of values at constant temperature. So, as you can see here, this curve is for absorption curve and this B curve is for desorption curve. You can notice hysteresis between these two, because after drying completes, again some moisture absorption by the product has been observed, and because of that these hysteresis are observed. Okay. So, in the horizontal axis it shows water activity, and in the vertical axis it shows water content. Okay. So, what it shows primarily, it has slight hysteresis in reabsorbing water when the product has been dried. Okay. So, this is how we got different sorption curve. Let us discuss about the method of drying. So, there are different methods of drying. So, primarily it has got two division, like active dryers and then passive dryers. Okay. So, as you can say, active dryer means you need to supply some kind of forces externally, and passive devices are something like natural circulation. So, again these active dryers can be classified into many groups, like direct, mixed mode, and again mixed mode with natural and forced, and again natural circulations can be divided into many groups, and these direct dryers are something like box type dryers, cabinet dryers, then tunnel dryers. Okay. So, there are different kinds of dryers. Okay. So, this figure shows the different methods of drying. Okay. So, let us discuss some of the drying devices which is used extensively historically. So, this is a cabinet dryer. So, solar radiation is falling through this glass cover, and materials to be dried will keep here in these trays. So, these are trays, so long trays. So, different stages are there for keeping the products, and air is supplied from the bottom. Okay. So, finally, air has to be take out. So, it will carry the moisture. Okay. And this can be taken out with time if we know the drying time for a particular material, right. So, forced circulation dryers are something like this. We have glass cover, solar radiation is falling through this glass cover, and materials to be dried will keep in these trays, and blower is employed here to suck the air. Okay, because it is a active device. So, external unit has to be employed to suck the air. So, drying is performed by using this sucking effect of this air. Okay. And this is one more forced circulation dryer, which is indirect grain. So, this is solar air heater. Okay. And blower is installed here. Blower blows the air. So, of course, we need to apply some kind of electricity to run this blower. So, air will flow through this air heater, and then it will introduce here in this bed. Okay. And feeding will be done here, and then drying product can be collected from the bottom of this vessel. Okay. And air can be ejected from the top. Okay. Normally, its capacity varies from 10 ton to 15 ton per day, and initial moisture varies from 11 to 14%, and final moisture after drying is about 5% is achieved for this kind of arrangement. So, let us do a calculation how this drying calculation can be carried out, which is very, very important. Once we are comfortable about this, then we can do any of the calculations. So, let us consider a problem. Say we need to dry a product, say agricultural product, maybe grapes or maybe other products. Say let us consider the mass of the product is 100 kg and initial moisture content is 75% and final moisture content is 14%, and we need to dry this product in 2.8 hours, and maximum allowed temperature is 70 degrees C and ambient temperature is 25 degrees C, right. So, now first step is to calculate the water removal. Okay. So, water that has to be removed, that is based on the wet material moisture content. So, which is known by us, this W is equal to W in minus W out, then 100 minus W out is something like this, 0.71 kg per kg of material. Okay. So, that is the water that has to be removed. Okay. So, that much of amount of water has to be removed. Okay. So, for 100 kg of product, so this is for single kg, the water that has to be removed is 0.71 into 100, it will be 71 kg for this problem. The amount of material to be dried in 2.8 hours will be 100 divided by 2.8, it will be 35.72 kg per hour. Okay. Now, we need to calculate what is the drying rate. If we need to calculate, then what we need to do, we need to multiply with this 0.71. Okay. So, what we get now 35.35 kg per hour is the drying rate, right. So, now we need to use this enthalpy humidity diagram, okay, or psychometric chart. So, for air at 25 degrees C and relative humidity of 60%, absolute humidity is found to be 12 gram per kg, okay, and enthalpy is 56 kilojoule per kg, right. And for 70 degrees C, relative humidity of 6.5, enthalpy is about 100 kilojoule per kg, okay. And also we need to find out this equivalent humidity, okay. So, because activity is about 0.57 in our case, so it will be equivalent humidity will be 100 plus 57 divided by 2, it will be 78.5. Okay. So, for mean humidity of this value, the air humidity at the exit of the dryer is 28 gram per kg and the corresponding temperature is 35 degrees C. Okay. So, we need to use those values for calculation of air needed for drying of 100 kg of raw material. So, if we have to calculate for 100 kg, then we have to multiply with 100. So, VAR, which is nothing but air needed for drying of raw material. So, since it is 100 kg, so we need to multiply by 100, then MW divided by density of air multiplied by XM minus XA, which are known to us now. This 12 is known and then we have 28. Okay. This is 28 minus 12 and these values are known. So, once we do the calculation, it is found to be 129.13 cubic meter per hour. Okay. Now, this heat needed to increase the drying air temperature from 25 to 70, that also you can calculate very easily. Okay. So, this can be calculated by using the values what we have now. So, Q is found to be this. Okay. For 2.8 hours, the drying period, the energy consumption is Q is about 19.52 megajoule. Okay. So, that much of heat is required to remove the moisture content from 75 to 14% if we consider 100 kg of this raw agricultural product. Okay. So, this energy consumption is 19.52 megajoule. Okay. So, this collector area required may be calculated from the heat required value. So, this value. So, once we know this value, then from that we can calculate the area required for drying the required amount, right. So, this collector area required may be calculated from the heat required value by taking into the consideration the solar collector efficiency and the corresponding heat loss. Okay. So, this is very, very important. Once we know this, then we can size the kind of solar air heater required and what capacity, okay, how to connect those solar air heater for meeting the requirement. Okay. Now, you can see this is a psychrometry and drawing curve. Okay. So, in psychrometry is the study of the property of mixture of air and water vapor. The psychrometric chart is a graphical representation of the physical and thermal properties of the atmospheric air. Okay. So, this axis shows the dry bulb temperature, this is the specific humidity, and we will have enthalpy is here. Okay. And all the parameters, these are the relative humidity lines. Okay. Specific volume is also here. Okay. So, at particular temperature say 20 degree, what will be the relative humidity? If we know the relative humidity say 40, okay. So, we can find out the coordinate, and if we have to know the enthalpy, then we have to go to here, then we can get the enthalpy. So, these charts are used for this kind of drying calculations and then psychrometric calculation. Let us now discuss how this solar air heater can be applied for process heat industries, okay, or say which require process heat, and we can store energy, okay, by using this solar air heater. So, this slide shows the use of solar air heater for process heat industries. Okay. So, this is a solar collector, this solar collector, solar radiation is falling on the collector, okay, and blower is used. Okay. So, blower forces the air and it goes to the dumper, and then we can store. If we have generated more than the required air, then we can store it by using a rock bed storage or some other devices. Okay. And whenever required, that can be used for process heat applications, right. So, sometimes we can use the exhaust of engine to harvest those waste heat for drying of some other agricultural products. At the same time, we can connect that system with the solar air heating arrangement. Okay. So, when solar is not there at the time also, this facility can be employed for generating hot air. And this is something called solar chimney power plant. Okay. As you can see, this is a very tall chimney and this is one turbine, okay, and these are greenhouse. So, solar radiation is falling on the greenhouse, and then there is a draft, okay, and then this turbine is rotating and electricity can be generated. Okay. So, actual installation seen something like this. So, this was suggested in 1970s and it was also known as solar updraft tower power plant, and it consists of a tall central chimney, this is the chimney, then circular greenhouse with transparent cover. So, this is the greenhouse and it is very, very transparent to the solar radiation, a metal frame to hold the greenhouse. Okay. So, here some kind of frame is required to hold the structure, and a fan and generator unit. So, this is not shown, this is a fan, but no, this has to be taken out, generator part has to be taken out, and then electricity can be generated. So, this sunlight passing through the transparent cover causes the air trapped in the greenhouse to heat up to 10 to 20 degrees C. Okay. A convection system is set up in which hot air is drawn up and continuously replaced by fresh air drawn in the periphery of the greenhouse. The energy contained in the updraft air is converted into mechanical energy by a turbine located at the base of the chimney. Okay. So, this is the turbine, and then into electrical energy by conventional electrical generator. So, we can generate electricity from the solar energy, right. So, let us take an example. So, this data is for an installation done at Spain. Okay. This is a pilot plant solar air electricity generating unit. So, its chimney is about 195 meter tall, okay, and diameter is about 10.3 meter. Okay. The solar collector area extended to a radius of 122 meter. Okay. It's a huge from the chimney, with glazing being 1.85 meter above the ground. Okay. The clearance is about 2 meter. Total area of the glazing is 46,000 meter square. Okay. It's a huge area. And as far as turbine is concerned, there are 4 numbers of blade of length 5 meters and rotated at a speed of 1500 rpm to produce a peak output of 50 kilowatt. Okay. The energy conversion efficiency of this kind of solar chimney is really low, and this maximum conversion efficiency can be calculated by using this expression. Once you know the height of the chimney and then ambient temperature, of course specific heat is known to us and G is known to us. Okay. So, by using that we can calculate what will be the maximum conversion efficiency of the solar chimney, right. So, we can solve this numerical. So, this numerical goes something like, with following assumptions and given data, calculate the maximum possible conversion efficiency obtainable with the chimney. Also estimate the efficiency of the plant as a whole and the daily electrical output in a typical summer month of solar radiation about 6.5 kilowatt hour per meter square. Okay. So, height of the chimney is given as 300 meter. Solar collection area of the greenhouse is 50,000 meter square. So, area is known now, CP value is known, TA is known, and assumptions are something like the turbine generator get converted only 50% out of the maximum available energy into the electrical energy, and second assumption is the collection efficiency of the greenhouse is 25%. Okay. So, eta max, we know the expression GH by CPTA. Okay. We can substitute straight away, and what we get, maximum efficiency is 0.96%, which is very less, right. And if we are interested about overall efficiency, which includes turbine generator and then collector efficiency, that has to be multiplied with this what we got here now. So, 0.25 is the turbine generator is the greenhouse efficiency, okay, and then turbine generator efficiency is 50%, so it will be 59, and this maximum efficiency is 0.96. So, there is multiply, then finally what we got, about 0.12% is the efficiency, which is very less, okay, compared to other solar conversion devices. So, this daily electrical output we can calculate now. So, which is nothing but 6.5, which is given to us, this value is given to us, solar radiation, then multiplied by area. So, this is something like I into A, okay, and then you have efficiency. So, this is like output, so something like QU, okay. So, that we can resemble. So, if we know this efficiency, then area is known, then intensity is known. So, we can calculate what is the daily electrical output of the plant, which is nothing but 6.5 multiplied by 50,000 multiplied by 0.0012 is equal to 390 kilowatt hour. Okay. There are other installations as well in other countries, like in Australia they have a plant of capacity 200 megawatt electrical, and its height was 1 kilometer and greenhouse collector area is about 7 kilometer in diameter. So, it is a huge structure. Okay. So, even though the efficiency is very low, but there are certain conditions at which we can go for this kind of installation, right. Now, let us summarize what we have discussed today. So, primarily we have discussed about the testing of solar air heaters, what are different instrument use and how this testing is done. Okay. So, this testing is done at different mass flow rates and at fixed air inlet temperature. Okay. Also, we have learned what are different instruments, like for flow measurement we need to use rotameter or maybe sophisticated mass flow meter. For temperature measurement we need thermocouples. So, we need to measure at different thermocouples for inlet and outlet temperature, and of course, we need to have some kind of mixing fans to regulate or to minimize the fluctuations of the temperature variations goes out from the solar air heaters, and then reconditioning unit. And also we have studied the application of solar air heaters in drying of agricultural products, and also we have studied drying characteristics curve, drying calculations by considering 100 kg of raw materials to be dried from 74% to 14%. So, we have understood the amount of heat required for doing so, and also we have studied the use of solar air heater for process heat generation or process heat in industry. And finally, we have studied solar air heater for power generation. Okay. So, I hope that you have enjoyed this video. Thank you very much for watching.